Alright gang, here we go. This is for Chem 2, Unit 7. We're talking about the fundamental gas laws. Should be a pretty easy short video. We're just going to kind of go over it, make sure we're all on the same page. Most of this should be reviewed from Chem 1. Okay, Boyle's Law. Alright, Boyle's Law. Essentially, sorry, just to take a step back real quick. Remember we talked about gases, we talked about pressure. Okay, anytime we're talking about gases, really we care about four specific variables. Okay, so we care about pressure, we care about volume, we care about amount, usually in moles, we care about the temperature. So these are the four things. So each of these laws that we're going to talk about is today, what we're doing is we're going to take two of those four variables, hold them constant, and then see what the relationship is between those other two. All right, so for Boyle's law in particular, this is the first one that we're going to talk about. The volume, okay, we're going to keep the quantity of gas constant and the temperature constant. So we're holding the quantity of gas and the temperature constant. So we're really just relating the pressure and the volume. And it says that the volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure. All right. So notice that as our balloon, okay, starts at the bottom near the earth and rises up through the atmosphere, the volume gets bigger because the pressure as we go up gets lower. And we know this as we go up in the atmosphere, our pressure goes down, so the volume had to have gone up. Remember, we used the vacuum pump at school in order to do this to our own balloon and possibly Marshmallow Man, okay? All right, so that's Boyle's law. So mathematically, this is kind of what it looks like, and this should look very familiar. P1V1 equals P2V2. Essentially what this says is that the pressure and the volume at state 1 is equal to the pressure times the volume at state 2. Okay, notice that we have pressure times volume is equal to some constant. This makes sense, okay, and because it's just a ratio, it's this relationship, mathematical relationship. Okay, notice that when we graph it, it looks kind of interesting, and you should be able to recognize this relationship. Okay, pressure and volume. If we graphed these straight up, just normal, we'd get this curve, okay, with volume in the y-axis, pressure in the x-axis. And notice that we get this non-linear relationship. However, if we flip p over and find the inverse of all of our p values, okay, we get a straight curve or straight line showing that relationship. So this is really what shows us that volume and pressure are inversely related to one another, because when one of them is flipped over, you get a straight line. And you could actually do it the same. You could have pressure by itself, and you could take the inverse of the volume and then graph it, and you get a straight line for that as well. All right, so that's Boyle's law. As pressure increases, your volume decreases. As your volume decreases, your pressure increases. That makes sense. Next one is Charle's law. Okay, and remember we have pressure, volume, amount, and temperature. Okay, so in Charle's law, it says the volume of a fixed amount of gas at constant pressure is directly proportional to its absolute temperature. Now, this is an important part I'll come back to in a second. But it says the volume of a fixed amount of gas, so we're holding this steady, constant, okay, and at constant pressure, so we're holding this constant. So really, Charle's law is representing or is showing the relationship between volume and temperature. Okay, and it says that the volume is directly proportional to the temperature. So as our temperature increases, the volume increases, and as the temperature decreases, the volume decreases. And this makes sense. So we could take this balloon, and if you've ever taken a balloon, stuck it in your freezer, you'll see that it shrinks. Okay, and in class, what we did is we took, an Erlenmeyer flask, got it with a balloon, covered it with a balloon, got it hot inside, and the balloon blew up as the gas got bigger, because we were at a constant pressure, because that balloon is a diaphragm that can change shape. Okay, but then we could also cool it down, and the balloon would go back smaller. And so as we cool it down and get it bigger, we change the shape of our balloon because the volume of the gas inside of it is different. All right. Now the trick here, this absolute temperature, this is an important value. Remember, whenever we talk about absolute temperature, really we're talking about Kelvin. Now the Kelvin part is important because remember, on the Kelvin scale, Kelvin cannot have negative values. It starts at 0, that's absolute 0. That's as cold as anything can get, or lacking of heat as anything can get, and it can go up from there. Okay. Whereas if we use Celsius, okay, we can have negative values. So this is a very important thing. Whenever we're dealing with gas laws, Okay, we always have to use Kelvin for our temperature scale. Always, always, always use Kelvin for your temperature scale. Okay, because if you use Celsius for your temperature scale, you can have a negative Celsius, all right, and then that would imply that you'd have a negative volume, which really doesn't make sense at all. How do you have a negative volume? It's just like, a black hole or something weird. I don't know. Okay, so here's the mathematical relationship of Charles' law. Okay, right here. So the volume divided by the temperature at state 1 is equal to the volume divided by the temperature at state 2. All right. Notice that once again we've got this constant thing. We've got volume times some constant times t, or volume equals some constant times t, and we can graph these and we get these straight lines here. Okay. Now notice they've graphed all these data points, put in a line of best fit, and then they extrapolated their line down to this value here. Now this negative 273 should look very familiar to you, right? That is equal to 0 Kelvin. Negative 273 is absolute zero. That's as cold as anything can get. So, but let's think about what this means real quick, just for fun. Okay, if we're at absolute zero right here, that means we're at this temperature on our Celsius scale, negative 273. But what does this tell us about our volume? Well, this means that our volume would have to be 0. Well, so this really explains, or at least gives one indication, one reason why theoretically it's impossible to reach actual absolute zero, is because when that occurs, Charles' law says that the only way we'd get to this value, okay, is if our volume was 0. Well, the only way you have 0 volume is if you didn't have matter anymore, right? Because matter is defined by two things. It's defined by having mass and taking up space, right? And if you're taking up space, that means you have to have volume. That's the whole idea. Okay, so that's one of the big reasons why we can't ever actually reach absolute zero, because we would only be able to have a temperature if we had mass that could have kinetic energy, right? But if we have mass, then we have some volume that we're taking up, right? And so you can't ever quite. You kind of get into circular logic. All right. Anyway. Next one here is Gay-Lussac's law of combining volumes. You might have also heard of Gay-Lussac's law as the relationship of pressure and temperature, and it looks very, very similar to Charles' law, right? P1 over T1 equals P2 over T2. And this is kind of a slightly different law, but this is a very similar law to Charles' law, so the textbook kind of glosses over it. Doesn't really talk about it, but this might be something that you've seen in the past. But this law here is slightly different than this one, okay? So it says at a given temperature and pressure, okay, the volume of gas that react with each other is in small whole numbers. Okay, so this is the important part, is when we're taking our gases and we're reacting them together, they always react in smallest whole numbers. Okay, for example, if you react 2 volumes of hydrogen gas and 1 volume of oxygen gas, they will make 2 volumes of water vapor. Okay, always in these small whole number ratios. Okay, and it's based off the stoichiometry, and we know this, that we can take hydrogen gas plus oxygen gas and we can form water. Okay, and it's always going to happen. We got to balance this thing, right? So we'll put a 2 here, 2 here. So notice that we've combined 2 volumes of hydrogen with 1 volume of oxygen. We get 2 volumes of the water out. Okay, stoichiometry based. So it leads to this overarching idea of Avogadro's law. Okay, and Avogadro's law states that the volume of a gas at constant temperature and pressure is directly proportional to the number of moles of the gas. So once again, we've got these 4 specific values for gases, okay, and it says right here we're keeping the temperature constant, and we're keeping constant temperature and the pressure constant, and we're relating volume and the amount or the moles of gas. Okay, and because of this relationship, we know that any gas at STP occupies 22.4 liters. Okay. So this is a really important value. Now, remember, these are the values, and they're really nice that they label them out here. This is your STP, standard temperature and pressure. Standard pressure is 1 atmosphere. Okay, standard temperature is 0 degrees Celsius, or 273 Kelvin, 273.15. Kelvin. All right, so it doesn't matter what kind of gas you have in it, how dense it is, how much mass it has, how complex it is. As long as it's a gas at STP, it's always going to take up 22.4 liters. Okay, and that's actually like quite a big space, right? A 2-liter bottle pops like that big. 22.4 liters would be 12 of those and then some. Right. So anyway, and then so mathematically, Avogadro's law looks like something like this here. So this is important. Okay. So V1 over N1 is equal to V2 over N2. And we can use this to solve different equations. All right. So we're just going to look over this real quick, just kind of using our general knowledge of these trends of gases and just kind of see if we can figure out what's going on. So it says, suppose we have a gas confined to a cylinder that has a movable piston that is sealed so there are no leaks. Well, that's nice. All right. It says, how will each of the following changes affect the pressure, the number of moles of gas, and the average distance between the molecules? All right. So for part A, okay, we are heating the gas while maintaining a constant pressure. Well, if we maintain the constant pressure, that means the pressure of the gas should be the same. So we'll just write same for AI. All right. And then part 2 says the number of moles of the gas in the cylinder. Well, we've let it sealed, right? Kept it sealed, there's no leaks, and we heat it up, but that doesn't change how many moles, so the number of moles of gas should also be the same. All right. Now we're on the third. Right? It says the average distance between the molecules. Well, average distance is really just dependent upon the volume, right? If we haven't added more things to it and we haven't taken away the space, okay, then our molecules have to, as our volume increases, the molecules will on average get farther apart. If the volume decreases, on average, the molecules will get closer together. Okay, so we're heating the gas while maintaining a constant pressure. Well, if we maintain constant pressure but we're heating gas, that means our volume had to have gone up. That's Charle's law, right? Heating the gas increases the volume if your pressure and your moles are the same. Pressure and moles are the same, the volume has to go up, right? So if the volume goes up, we got the same number of moles of gas, so the average distance between each of those molecules has to have gone up, so it would be increase. Okay. All right, let's try part B here. So B, all right, B says reducing the volume while maintaining a constant temperature. Okay, so constant temperature, and we're also, so notice that again, we're going to keep the number of moles constant. So if we're reducing the volume, then what will happen to the pressure? Well, the pressure and volume are inversely proportional to one another when temperature and number of moles are the same. All right, so that means if the temperature, or the volume, if the volume goes down, that means the pressure had to have gone up. All right, so that's just Boyle's law. All right. Part 2 says the number of moles of gas, well, we're not adding anything, so therefore that has to remain the same. All right. And then for part 3, it says, where is it? The average distance between the molecules. Well, the volume remains the same. Where the volume decreases, right? So those molecules have to be getting closer and closer and closer together. So therefore, the average distance between these molecules has to decrease. All right. Last one here, part C. It says injecting additional gas while keeping the temperature and volume constant. All right, so if we inject additional gas while keeping the temperature and the volume constant, what would have to happen to the pressure? Well, the pressure would have to increase because there's going to be more collisions against the outside of the container. So that would be an increase of pressure. Part 2 says the number of moles of gas in the cylinder. Well, that's going to increase, right? If we're adding more gas molecules, the number of moles has to increase. That just makes sense. And then last one here, part 3, says the average distance between the molecules while injecting additional gas. Okay, what will happen to the average distance? But we're keeping the volume constant, right? But we're adding more things. Okay, so it just makes sense that these gas molecules would have to be getting closer and closer together. So this average distance would have to decrease. All right, so those are your basic gas laws. In the next video, we'll talk about ideal gas equation and a couple other important things dealing with it. All right, good luck with your homework problems. Let me know if you have any questions, and I'll see you on the flip side.